My name is Dominik Ślęzak, and this is my great pleasure to chair two keynote talks today. The first speaker is Dr. John Sowa, who spent 30 years working on R&D project at IBM and is a co-founder of the VivoMind Research company. He has a BS in mathematics from MIT, an MA in applied mathematics from Harvard, and PhD in computer science from the University of Brussels. He is a fellow of the American Association for Artificial Intelligence, and he has published several books and many articles on artificial intelligence, computational linguistics, and related areas of cognitive science. With his colleagues at VivoMind, he has been developing novel methods of learning, reasoning, and language understanding. The system of conceptual graphs, which he designed, has been adopted as one of the principal dialects of the ISO IEC standard 24707 for common logic. Let me add my personal observation. I met John first time last year in Warsaw. He was a keynote speaker at Web Intelligence Congress in Warsaw, and we are really very happy to have him again in Poland and to listen to his new ideas, new research results, and just get inspired by his innovative thoughts. John, the floor is yours.
Well, thank you very much. That was great. Now, one thing I'd like to mention is that these slides that I'll be presenting right now will be on my website next week. I just finished them this morning, so they're not yet there, but by next week they should be there, and you'll be able to get some of them. There is, at the center, is the philosopher Charles Sanders Peirce, who was a pioneer in logic and also in semiotics, the theory of signs, and a number of related areas. And one of his major branches of philosophy is pragmatism, which is very different from the branch that his friend William James developed. It's related but different. And one of the things that Peirce emphasized is the logical foundations of induction, abduction, and deduction, and how they work together in a cycle which he called the logic of pragmatism. Now, I'm going to go into more detail about how this is related to all of artificial intelligence and cognitive science and everything else, and I'll do this all in about 40 slides. So if you want to see the slides, they'll be on my website next week. Okay. Now, the outline of the talk, first I'm going to talk about some problems and challenges for artificial intelligence. These were the great promises back in the 1960s that didn't quite make it, and we're still trying to meet the challenges and solve the problems that were stated way back then. Part two, I'll talk about what kinds of things are possible today. I want to talk about visualization, and one of the major problems is how do you relate thought and language to vision, because vision is the primary sense that people use for their mental imagery and planning and everything else. And some people have been claiming that logic is the foundation for language, and that's upside down. Vision is the foundation for language, and language is the basis for logic. Every version of logic is a simplified version of ordinary language. Simplified, stylized, and disciplined. Discipline is important, but one thing that Peirce added, Peirce was a founder, one of the pioneers in logic, but he said one thing that deduction can never do is introduce anything new. Deduction can derive the consequences of what you already know, but it cannot introduce something new, and you need the other methods in order to really bring in what's new. And so that leads to the cycles of learning and reasoning, which is part 4. Okay, so the first problem is that the early hopes for artificial intelligence have not been realized. And one of the things that I often emphasize is that a 3-year-old child is better able to speak and understand language than any computer system today. And for learning, a 3-year-old child is superior to every adult on the planet. So as far as learning languages, children are the experts in learning. Adults are okay, but not quite as good, and computers are way down at the bottom. And another thing is that even animals can perform tasks that are impossible for the best robots we have today. So the question is, what do we do about it? How can we make things better? Well, here's a quick summary of some of the early achievements. In 1960, Hao Wang developed a theorem prover that took 7 minutes to prove all 378 theorems in first-order logic in the Principia Mathematica. That is the book by Alfred North Whitehead and Bertrand Russell, two brilliant logicians, and all 378 theorems that they proved, the computer could prove in 7 minutes. Now that was an old vacuum tube computer. Its total memory was 144K, not M or G or anything else, 144K of bytes of storage on that computer, and in 7 minutes time, that's the total CPU time to prove all 378 theorems. Now, Whitehead and Russell took a lot longer than that. Now, in 1960, Émile de Lavernay wrote a book on machine translation in which he said, while a great deal remains to be done, it can be stated without hesitation that the essential has already been accomplished. Now, if anybody here has ever used Google Translate, you can realize that it's not quite done even yet. In 1965, Irving John Good, a statistician and engineer, speculated that says, it is more probable than not that within the 20th century an ultra-intelligent machine will be built and that it will be the last invention that man need make, because everything else can be done so much better by the computer that once they do that, it will solve every problem. Well, he claimed that before the end of the 20th century. Well, that was 16 years ago, and we're still very far from there. Marvin Minsky, another pioneer in artificial intelligence, was a technical advisor for the movie 2001. That was the space odyssey with going out beyond Jupiter, and said that the HAL 9000, Marvin Minsky was an advisor for that project. He said the HAL 9000, that was that computer there, he said it's a conservative estimate of the level of artificial intelligence in 2001. Well, it didn't make that promise either. Now, here's one of the early success stories, sort of successful, partially successful. This is the perceptron. The perceptron, which was developed by Frank Rosenblatt in 1957. And originally it was a software simulation, but then they designed a Mark I, was a hardware version founded by the US Navy. And this was corresponds to a one-layer neural network. And there's the layer, the association area. That corresponds to what today is called the neural network. And it was just a one-layer network. And the point is that it was actually fairly interesting for a lot of applications. And there was a press conference on this in 1958. And the first version, the hardware version, was funded by the US Navy. And the New York Times reported that the perceptron was going to be the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Well, it's not quite what we have today, but it was very interesting for the day. In 1959, Art Samuel, who was working at IBM at the time, had invented a very interesting, there's Art sitting at the console of the IBM 7090 computer, and there's a checkerboard, and he designed this machine to play checkers. And it was running first on the 704, that was the vacuum tube machine, later on the IBM 7090. The 7090 was comparable in speed to the original PC. The original IBM PC was about the same speed as the 7090. The maximum memory of the 7090 was 144K bytes. But the program used an algorithm for learning that was sort of like a perceptron. It was about the same capacity as a perceptron, and he used that for evaluating game positions. But the important point is that it was a hybrid. It did not use just a perceptron. It used the alpha-beta algorithm. Those of you who studied AI and things like that, you know about searching game trees and all, and the alphabetic algorithm was originally designed by Art Samuel for this program. And with that program, it does the deep, deep searching. Now, it only searched a few levels deep, but with that ability, it was able to win at least one game with the Connecticut state champion. The computer could beat Art, the inventor, and it was able to beat the Connecticut state champion at playing checkers. Now, with these achievements, that's why people made these wild predictions that, hey, if we can do this already with the technology around 1960, imagine what could be done 40 years later or 41 years later by 2001. And so they just projected this massive increase. Well, there was a massive increase in hardware. The hardware capability just went up exponentially, but the software did not. And the question is why? Why isn't the software exponentially increasing while the hardware was exponentially increasing? Good question. One problem was the bird nest problem. And I mentioned that birds were better in some cases than the best robots we have today. And the point is that the robots are very precise. They work very precisely in doing what they do. You can guide it by its hand. You can take your hand and guide the robot's hand, and it will repeat exactly the same motion with perfect precision. But the point is that it cannot do what a bird does, namely build a tree and build a nest in an irregularly shaped tree with pieces of straw and twigs that are irregular, and it will find all kinds of pieces of whatever, put them together, and build a nest. And no robot today can do what a bird can do. And that's a critical point. There's a lot of things that robots cannot do. Now this is a cartoon. This is a cartoon from, you can search for it if you want to see this. And anyway, it shows all the characters in this are, all the characters in this cartoon happen to be represented by birds. And as a Sowa myself, I sort of sympathize. Anyway, so here's the, here on the left-hand side, the client comes in and says, what's it going to take to get this thing moving again? Now, we know a little bit about cars and fixing them in a garage, and the bird on the left looks like a repairman, so he looks like the man who's going to be the auto mechanic who's trying to fix it. And what he answers is, parking on a hill and releasing the brake. Now, this is something that anybody who knows anything about cars can understand what's going on here. And if we try to do this by computer, the first part is actually quite easy. Parsing the question and the answer, both the English question and the English answer, are fairly simple, and programs, computer systems back in the 1970s were good enough to analyze those questions and get the grammar correct. However, it's much, much harder is to use the background knowledge in order to recognize the situation. How do you recognize that this client here is going to a garage? And also, how do you recognize the picture? This is a car. But how do you recognize that this is the engine and this is the hood? And over there you see a few more parts of it. But it doesn't look like a typical car. And if you have these vision programs that are trained to recognize something by vision, it's not really going to recognize these things as a car unless it has a huge amount of knowledge about the various parts of a car and how they fit together, and how in a garage where they're repairing it, they have the hood up, and there's somebody here who's wearing working clothes that is probably the one who's going to fix it. There's a lot of detail there that is beyond the capacity of any learning system we have today to recognize this. Also, doing the semantics. It says, the question is, what's it going to take to get this thing moving again? Lots of things over there. What thing is meant? And how do you relate the word thing to this picture and to recognize that what this bird is talking about is a concept car? And how do you determine the answer? It says, what's it going to take? What does he mean by take? The verb take has a large number of possible meanings. In this case, he's probably asking how much money would it cost. How do you recognize that what he's asking there is about how much work is involved, how much money is going to be involved, and then once you understand all that, then the auto mechanic on the right-hand side is saying, park on a hill and release the brake. Now, that will get it moving, but not the way you want it to. I mean, usually when you're on a hill, you do not want it to roll down, and if you do let it roll down, it's probably going to crash, and it's going to be even worse. But the point is that this was a cartoon, and it's a comic strip, and so that's ironic and humorous. How do you recognize irony? How do you recognize, first of all, you have to recognize the literal meaning, then you have to recognize what is expected in that context, then you have to recognize that what would happen is something you don't want to happen, and therefore it's undesirable, therefore it's ironic and humorous. All of that is far beyond the capacity of any of our computer systems today. So that's a major problem. Now here's Google Translate. And this was an example that was published recently, and they had sentences in English translated into German, and by using Google, and I added the Polish translation, and the problem in Polish and German is identical, and the point is that the first sentence, the electrician is working, and the second example, the telephone is working. English uses the same verb to work in both cases, but German and Polish use different verbs. So in German, der Elektriker arbeitet, and in Polish, elektryk pracuje. So in the word arbeitet and pracuje are the ones that you use for human, and then the telephone is working. Der Telefon funktioniert, funktioniert in German, and telefon działa in Polish. So you use a different verb for a telephone or other kind of mechanical device than you would use for a human being. So for a short sentence, Google is fine, because what it does is just look at what they call n-grams. That's n words in a string, and they just count up have a window of a certain number of words, and within a small window, it works fine. But if you have a longer window, if you have a longer sentence, you have a problem, because look at that. There's the electrician that came to fix the telephone is working. Now there you have telephone right next to working, and so what Google will translate in German, it comes up funktioniert, and in Polish działa, because these two verbs go with telephone, but really it should be going with electrician. And in English it says the telephone on the desk is working, and here there's no person mentioned. However, the word telephone is way at the front, and so it uses arbeitet in German and pracuje in Polish to make that connection. Now that's a problem. Now notice, by the way, that this is today. I just did this last week to check out what German and Polish translations would be, and it still today is not doing that. Now, this kind of problem would be solved by a system that used parsing. If it parsed a complete sentence, according to the technology of the 1970s and 80s, it would be able to get the correct verb. However, Google does not do that because they're trying to do a huge volume of translation by statistical methods, and they do it relatively fast. They don't want to take the time to do a detailed analysis, because if they try to do this kind of analysis for everybody who types their little question in, it would just overwhelm their computers. So they do this very fast method, which is useful. It's better than nothing, but it's really not accurate. Now here's an example of a 3-year-old child. This is a child named Lara who was being studied at one of these psycholinguistic tests. And usually what happens is at a university, they'll have a daycare center, and so the parents might leave their children off, and during the daytime, the psychologists have fun with the kids and trying their test out how they're doing. So in any case, this is the example of Lara. This is at the age of 30 months. So this was just before, 6 months before her 3rd birthday. She was able to say, here's a seat. It must be mine if it's a little one. I went to the aquarium and saw the fish. I want this doll because she's big. When I was a little girl, I could go, geek, geek, like that, but now I can go, this is a chair. Now, that's an amazing amount of knowledge and ability for just a child just before the age of 3. Now, Lara was a bright child, and she probably was familiar with psychiatrists and psychologists studying her language, so she knew about talking about language at earliest stages, and so she's talking to a psychologist, She knows the psychologist is interested in language, so she was explaining to the psychologist what she knew about her own speech, that she used to say, geek, geek, but now this is a chair. Now this is an amazing amount of language and logic. Look at that. If, there's an if statement. There is a because, there's when, and but now, and a contrast between when I was a little girl, but now. An amazing amount of sophistication at an age of 30 months. No computer system can do this today. And that's the question, why not? Here is Psych. Now Psych is a project that was founded in 1984. And so for over 30 years, they've been working on trying to encode as much knowledge as they could in logic. And the idea was to implement the background knowledge of a typical high school graduate. And what the ultimate goal was to learn new knowledge by reading textbooks. And after the first 25 years, they had spent $100 million and 1,000 person years of work. Now, that's 1 millennium. Can you imagine one person working for 1,000 years? That's the amount of work that went into designing this building the system, defined by 5 million axioms, 6,000 micro-theories, and yet it cannot learn by reading a textbook. It cannot understand language as well as a child. Okay, that's a problem. The neural nets, they're now calling them deep learning, but they're certainly not as deep as Laura at the age of 3. And here's the, this is not just a single layer neural network, but multiple layers. And Geoffrey Hinton, who is the founder of this whole branch of neural networks, claimed that this is a universal algorithm for computer systems. And well, it's universal for a low-level kind of thing, but it's certainly not universal for everything. And here's an example. Some of the students founded this company called DeepMind, and they had a system learning to play computer games, not just checkers and chess, but the early games on the Atari. And so one of them is Pong, Breakout, Space Invaders, Sequest, and Beam Rider. These are 5 games that it learned to play, and actually there were 7 games altogether. It had made no prior knowledge about objects, actions, features, or rules. The bottom layer started with pixels, a 210 by 160 video, and the game score. Each layer learns features which represent the data at the next layer, and the top layer determines which move to make at each step of the game. So the point is that it was able to play, to learn to play these games, and starting from no knowledge at all except the patterns. And then it was told whether it won or lost. And from that knowledge, it tried to figure out what rules and how to play. Now, the point is that the results on these games, it outperformed all the other machine learning systems around. So it was better than previous machine learning systems. It was better than a human expert on 3 of the games. These are Breakout, Enduro, and Pong. On another game, this is Beam Rider. It was close to human performance, but on those games that require long-term strategy, Qbert, Sequest, and Space Invaders, it was much worse than humans. Now, anybody who plays Space Invaders knows that you do have to have some practice to play well, but it certainly doesn't have a very deep strategy. It's not as deep as checkers, far less than chess, far less than Go, far less than bridge, and those games that people play require a huge amount of learning, but to claim that this system, which people learn relatively quick, this system was not able to play very well. So the point is that Samuel's system for checker playing was better than this system, even though Samuel's system had a much simpler learning method, but it was a hybrid. It combined the learning component with the alpha-beta search that those of you who studied it, and that's the deeper search that is used in games of chess and checkers for doing a deeper analysis. And the point is that a hybrid system that supplements the neural network with a more conventional kind of search can do much better than a system that uses only the neural network. Okay, so now the question is, what's possible today? And today, there's a huge toolkit of techniques and algorithms that are used in artificial intelligence and computer science and related things. So there's all kinds of things. There's parsers and translators that are much better than what Google used. Now, it's not that the Google people didn't know these things. It was that rather that they were trying to use a very simple statistical method, which by itself would have been a lot better if they added a parser in addition. Also, there's a lot of background knowledge in Wikipedia, grammars, like DBpedia, linked open data. The semantic web has a huge amount of information. If they could use that background knowledge, they'd be far ahead. There's theorem provers that are much, much more powerful than the ones that Hao Wang used back in 1960. Qualitative reasoning, case-based, analogical, statistical, connectionist, neural networks, pattern recognition, data mining, graph data mining, genetic algorithms, and all sorts of thousands of different tools and implementations and algorithms in the toolkit. But the problem is that a lot of these systems just use one paradigm, just one kind of method. And what people do is use a whole range of methods. People use many, many, many different kinds, and they integrate them in a single combined system. And now, Art Samuel's system, by combining alpha-beta search plus a perceptron, did much, much better back in 1959 than these deep neural networks today. Today, the deep neural networks are much, much better at pattern recognition than a perceptron, but they're not as good as even a perceptron plus an alpha-beta search at playing a game. So those are the problems. Now the question is, what makes people intelligent? And the short answer, people are very flexible, very general, and very adaptable. Now Marvin Minsky, who made those wild predictions back in 1968, he has learned a bit about the problems, and well, he always knew quite a bit about the problems, but he learned to be more cautious in making predictions. And one of the points that I think is very correct here, he said, what magical trick makes us intelligent? And he said, the trick is that there is no trick. The power of intelligence stems from our vast diversity, not from any single perfect principle. Our species evolved many effective, imperfect methods, and each of us develops more on our own. Eventually, very few of our actions and decisions come to depend on any single mechanism. Instead, they emerge from conflicts and negotiations among societies of processes that constantly challenge one another. And I think this is the key to understanding why these single paradigm systems really have not worked, because they only use a single paradigm. What you need to do is to combine all of the paradigms. The question is how? How do you design a system that can combine multiple algorithms and trade off one for another, and decide when to switch between one and another, how to use it? Now, Art Samuel's system made a simple trade-off. They only had two methods, and the one method, the perceptron-like method, was used for recognizing and evaluating the position, and then the other method was used for deep learning, for deeper search. And so the combination of the two was much more powerful. How do you design systems that can automatically determine which algorithm, which paradigm, and how to combine them automatically? That's the big problem. And now, an example is Cyc and versus the IBM Watson program that played Jeopardy. And the question is, why did IBM beat the Jeopardy champion instead of Cyc? Cyc had put 30 years of work into developing this system, and they had put in a huge amount of background knowledge. But the point is that it did not have exactly the right background knowledge and exactly the right way of putting it all together. Now, the point is that the IBM program had multiple paradigms. Cyc is based on a single paradigm: formal logic, deductive reasoning, a very large ontology, and large volumes of data. That's very useful by itself, but IBM used a team of researchers with a large number of different methods. There were about 36 people altogether that worked on this system, and they, each of them tried different tools, and they had developed many independently developed tools and made them interoperate on this particular problem. But they designed it for playing Jeopardy. Now what we want is a system that will have large numbers of tools and methods, but can be automatically put them together upon demand as required. So the question is, and also, we don't really have for each problem, we can't depend on 3 dozen PhD researchers to solve every particular problem that anybody might have. So we want a general purpose system that doesn't have to rely on each piece being designed independently and fitted together for these problems. So here's an approach that was done by Chris Manning and his students at Stanford. And they've been using statistical methods, but they've also been using hybrid methods that combine various kinds of things. One of the things they've been doing is to add the parsing. So they're using parsing methods which are 1970, 1960, 70 technology, and they're taking that technology and combining it with the neural networks and with statistical methods. So here's an example here, is a little picture, and the deep neural networks can recognize various parts: grass, people, building, tree, and various parts of it, segments, and recognize how they fit together. And then you have a sentence: a small crowd quietly enters the historic church. And there's a parse tree where it's analyzed according to a small crowd quietly enters the historic church. And then it puts them together and relates them. So that's better because it is now using a multiplicity of methods. Multiplicity of methods that you combine are better, but there's a lot more that needs to be done. Now, Minsky wrote, this is in 2004, Minsky and some of his colleagues designed this table, and it showed the various kinds of methods that traditional computing uses fairly easy. By easy, that means the kind of thing that any typical programmer can do. And there's an acronym, ASMOP. So anything that is not artificial intelligence is ASMOP, which means a simple matter of programming. Now that programming might take, might take a whole. If you're building the Microsoft Windows, it might be thousands of people working together. But it's a simple matter of programming, ASMOP. That's considered easy. So anything that's not easy is classical artificial intelligence. That's the kind of stuff that was done in the 60s, 70s, and 80s. And now there's a lot more methods that people have developed, but there's still a need for better representations because there are still problems here that are intractable. Well, the point is, well, let's see, there's a lot of material here, but the point I want to make is that the ability to make tools is a critical test of intelligence, and at one time they say that's what distinguishes human, is that humans can make tools and use them. But now people are discovering that birds and that every animal has built-in tools, like the beak of a bird and the claws of a lion, and the point is that the animals have a lot of built-in tools, but they also can learn to make new tools themselves. And people, and the scientists now discovered that chimpanzees and birds and many, many different animals do make their own tools in order to build their things, but they have limitations in what they can do. And the point is that Minsky was making the point that for every physical tool or activity, there's a kind of mental tool. So the mental agents correspond to the diversity of human activities. And Wittgenstein had this idea of the language games, and the language games result from the many different ways of using the human vocal tools for talking about those activities. So we need ways of building hybrid systems that put together multiple methods. And we need methods of visualization. So we need methods of visualization. Mental models of visual things are more fundamental than language or logic. Computers can manipulate symbols faster than any human. The question is, but the point is that computers are not very good at vision. They're getting better than they used to be, but there's still a huge amount of work required for integrating vision and language, and that is a major challenge. And here's an example of American Sign Language, and there's the sentence, there's a sign for many deaf learn agent, that would be learners, enter, speak, college. And that sentence, that would correspond to the English sentence, many deaf students enter hearing colleges. Now the order of signs in American Sign Language is similar to English word order, but there are many syntactic features that are absent and others are different. Now one of the important points about the spoken languages and the sign languages, they use the same parts of the brain. There's Broca's area, which is primarily used for generating speech, is also used for generating the gestures in sign language. And the point is that it's not just used for speech. This is one of the studies by Laura Ann Petito, who studied infants, bilingual infants. These are infants that are bilingual in different languages. So she studied all pairs of 4 languages. Now this was done in China, or not in China, it was done in Canada, where they had lots of French and English speakers, and she had found pairs of parents for English, French, American Sign Language, and Langue des Signes Québécoise. So there were all 4 language and all 4 combinations. One parent spoke one or signed with one, and studied what the babies would learn. And they discovered that both monolingual babies and bilingual babies go through exactly the same stages and at the same ages for both spoken and sign languages. A hearing baby is born to profoundly deaf parents. The babies babble with their hands, but not vocally. So babbling is not innate. It's what the children learn, start doing at a very early stage when they primarily hear spoken language. If they have 1 or 2 parents that are both deaf, they start babbling with signs. And they start their babbling at a very early stage with signs. And the point is that for all of the babies, whether they're bilingual in 2 different sign languages, 1 sign and 1 vocal, or 2 different vocal languages, the point is that at every stage of learning, they express themselves with equal fluency in both languages. So they're learning them in parallel equally, and they go through the same stages. What this means is that the language methods of the human brain are not really designed for spoken language. They apply equally well to sign languages. And so the fact that we speak a language or sign a language, the results are the same. And in fact, you could say that probably the signing is more fundamental, and that's what some people have claimed, because they find that chimpanzees communicate very well with signing, even though they don't speak. So the point is that there's a spatio-temporal sequence, that in both signing and in spoken, there is a time sequence, and you have to combine both. Now, another point about visualization is that people say, oh, well, in mathematics, you have to do formal proofs. That's essential. Well, yes, proofs are important in mathematics, but they're not as important as visualization. And this is by Paul Halmos, a mathematician who wrote some textbooks that are widely used by mathematicians. And he said, mathematics, this may surprise or shock some, is never deductive in its creation. The insight never comes from a formal proof. Actually, you might learn quite a bit by studying a proof after you've already proved it. But the insight to get the proof, to discover what to do, that comes through visualization. And the mathematician at work makes vague guesses, visualizes broad generalizations, and jumps to unwarranted conclusions. He arranges and rearranges ideas before he can write down a logical proof. The deductive stage, writing the results down and writing its rigorous proof, are relatively trivial once the real insight arrives. Albert Einstein said the same thing. He says that words or language, as written or spoken, do not play any role in my mechanism of thought. And he said the psychical entities are signs, more or less images, and this is conventional words or other signs and other symbols of mathematics have to be sought for laboriously in a secondary stage. Okay, so visualization is fundamental to mathematics. The writing down a proof, that's important to check to make sure that you're right, but it's secondary. And this is Archimedes, the eureka moment, where he steps into the bathtub and discovers that a submerged body displaces an equal volume of water. And he discovered this by vision, not by proof, but once he had that proof, then he discovered how to compute the volume of this gold crown. The king wanted him to determine its volume, and he couldn't compute it, but he found that, oh, once you just submerge it in water and measure the displacement. And this is another one of Archimedes' insights, determining the value of pi. And Archimedes had two insights, both of which are visual. One is that the circumference of the circle is greater than that of the inner polygon, and it's less than that of the outer polygon. That's the first insight. The second insight, as the number of sides increases, the inner polygon expands, and the outer polygon shrinks, and they converge to the circle. Now, with those two insights, Archimedes used 90 sexagons, and he computed pi. The value he got was 22/7. 22/7 was the value that Archimedes discovered by using 90 sexagons. And later mathematicians used much larger polygons in order to compute the value. But the point is that the insight was visual. Now, once he had the visual insight, any good mathematician could compute the answer. But the creative process is the visual part. Doing the proof, that's simple. Euclid's proposition number 1. It says, on a given finite straight line, you draw an equilateral triangle. Well, the only thing that you're given in the statement is that you have a straight line, and you want an equilateral triangle. Nowhere in the statement of that theorem does it say that you're supposed to have circles. So the critical insight here is to draw these two circles. And once you draw these two circles, draw one circle with a center at A, another circle with center at B, and then the point where they intersect gives you the triangle ABC. And that triangle you can prove. Once you have that insight, the rest is trivial. And that's the point of every one of Euclid's theorems. There's a diagram. And the mathematicians who tried to eliminate diagrams were going in the opposite direction from where they should be. The fundamental question is, how do you integrate diagrams into your proof? Because that is the fundamental issue of how people learn and how computers are going to prove things. They have to be able to work back and forth between the diagram. Without the diagram, finding that proof is very hard. Once you have the diagram, the proof is trivial. And so the question is, how do you find the diagram? Here's two games of Go and Go Moku. They have the same syntax. You start with an empty board and you just put stones around on the board. In the one game, what you do is you try to surround territory. That's in Go. In Go Moku, you try to find 5 in a row. And notice that the syntax of the two games is identical. Just put one stone, take turns putting stones on the board. But in the one game, where you have the goal to surround territory, guess what? That is the one that gives you the stones end up in that position. The one where you're trying to get 5 in a row, the stones end up in that position. And this is the point, that the final goal of the game, where you keep score, that comes at the very, very end. But the fact that you're going to evaluate your score based on the way that you evaluate the score at the very end of the game determines every move from the very beginning. Right from the first move, you're already planning for the end, which might be, in Go, it might be several hundred moves later. In Go Moku, it might be just, might be about 20 moves later. But the point is that right from the beginning, every move from the beginning, the purpose of it is determined by the score at the end, not by the syntax of how you organize it. And let me get on to the point that human learning requires language, and I'm going to get to the cycles of learning and reasoning. The point is that, children learn language by starting with words and patterns of words that are grounded in perception and purposive action. Purpose is fundamental. And a lot of philosophers that were trying to eliminate purpose, people say, oh, that's homomorphic. No. Purpose is zoomorphic. In fact, even more primitive than that, phytomorphic. Even plants have a purpose. Even a bacterium, and they say that the beginning of purposive intentionality is when you see a bacterium swimming upstream in a glucose gradient. that that normal physical causality would cause things to go downstream, but when you see a bacterium swimming upstream, there is purpose. And that's the point that Charles Sanders Peirce made, that the beginning of life is the beginning of intentionality. And it gets more complex as you go up. But that's where intentionality begins. And anything having to do with any living process or any robot that's trying to simulate a living process must begin with purpose. And the attempt to eliminate purpose, you know, some people say, oh, purpose is homomorphic. Or no, it's not homomorphic. It's not anthropomorphic. It's essential to every form of life from the bacteria on up. And you must have purpose. And the point is that you have the observations generate low-level facts. Induction derives general axioms from multiple facts. A mixture of facts and axioms is an unstructured knowledge soup. Abduction selects facts and axioms to form a hypothesis. You pull a hypothesis out of your soup. And this button, the buttons are so close together. And then deductions from it. Analogies may relabel a theory from one topic and apply it to another. Deductions from a theory generate predictions about the world. Actions test the predictions against reality, and the effects of the actions lead to new observations. This is the cycle that Peirce had emphasized as the logic of pragmatism. And he didn't draw this diagram, but I did. And it's, but the point is that this diagram, or a similar diagram, has been repeatedly rediscovered by many people, and they observed that you really must have for intelligence, you must be grounded in the observation. You start with the world, and from observation and induction, you get new information that goes into your knowledge soup. By abduction, you pull out fragments which you organize into a theory, which is a nice, crystalline, precise, elegant theory. And then by belief revision, you revise and revise. By deduction, you make a prediction. That prediction tells you what action to perform. You test the prediction by performing an action on the world. You observe the results, and you keep on going around and around. That's the human cycle as described by Peirce, and he made the point that this same kind of cycle would be for any kind of intelligence, whether it's human, alien. Peirce wrote a pioneering article on artificial intelligence back in 1879, and was one of the pioneers. He was already thinking about intelligent machines way back then, because they had some early logic machines that he was trying to generalize from, and Babbage's system, and he was thinking about that way back when. And he was making the point that this would apply to any kind of intelligence. And the knowledge soup is this, the totality of everything you know. And here's another thing. This is John Boyd. John Boyd was, he was an airline pilot, or not an airline pilot, he was a military pilot, was training other pilots for the Vietnam War, and he was discovering how to, and he had discovered these same steps of the 4 steps that you have to think in order to do everything from response at the second level, at the level of seconds, minutes, or hours. The idea is that you have an observe, orient, decide, and act, and repeat. Observe, orient, decide, and act. And Boyd made the point that these 4 steps are essential in every kind of thought, any kind of planning, from just fighting at a millisecond level in guiding your airplane, up to the level of minutes, to hours, to days, to weeks, to months, and years of planning anything. You have these cycles. And over the years, Boyd added more detail to it, and added this to all of the areas of observe, orient, decide, and act, and called it the OODA loop, O-O-D-A, observe, orient, decide, act. And the steps that he had are basically the same steps that Peirce had, but he developed it independently. This is by Stellan Olsen, who wrote a book on computer learning systems, and he said that this is the kind of processes that humans go through in learning, and also your computer systems must go through the same kind of processes. And again, he had different labels for it, but he had the same basic ideas, that you have your motor action, which has a physical causation on the world, on the physical causation on the environment. You observe, perceive the outcome. You have higher order representations, and you develop your representations, combinatorial generation. You generate a higher order theory, and from that you make a decision which guides some action. And so it's the same basic ideas labeled differently. All of these, now actually Olson refers to Peirce in several places in his book, so he's probably had read some of Peirce's work, so it wasn't totally independent. But here's James Albus was an engineer who had studied neuroscience, and he used ideas from neuroscience to design computer systems, and also that could do a similar kind of, could guide robots. And he had a very similar diagram. At the bottom he had the world, and with sensors that observe things from the world, the sensory processing that goes to build your models, with the world modeling, value judgment, your knowledge base, and then the behavior generation with the task knowledge, and then the various executions, and that goes to your actuators, which perform some kind of operations on the world. And again, he was relating this to the brain and to the kinds of circuits in the brain, to the kinds of operations, and he made the point that this kind of a cycle is essential for organizing how all the other pieces fit together. And here's another one of his the diagrams from Albus. And this work has stimulated a lot of work, the real-time control systems that has been used by various projects in NASA and others for guiding some of these missions that go perform the operations that are, when you have a rover on Mars, it takes 20 minutes to send a message back and forth, and in that time, the rover has to make its own plans. It doesn't make a major plan, but it makes little plans of what to do, because it can't get detailed instructions in the time that it has to wait. So it has to, the humans can't give a real-time control. They have to tell it a high-level plan, a high-level goal to achieve, and then the rover has to deduce all the steps that has to be achieved in the circumstances it happens to be in. And so it's very important to do this kind of work. And here are this is some more of the work that Albus had. So James Albus, as I mentioned, began his career as an engineer at NASA, and he worked for many years and published a number of letters, a number of articles and on this kind of method. And basically, his goal was to reverse engineer the human brain. And he made it very clear that nobody really knows how the brain works, but what he emphasized the importance of applications using the basic knowledge that is observed to adapt, apply, and integrate insights from artificial intelligence, neuroscience, and engineering. And one of the points he confirmed is the claim that Minsky makes about requiring multiple paradigms. You can't do it with just one algorithm alone. You need a large number of different methods, and the point that Albus was making is that a cycle very similar to the cycle that Peirce had observed 100 years ago when he was doing his work on logic and semiotics. It's very similar to the work that Stella and Olson did based on work being done in artificial intelligence. Very similar to the work that John Boyd observed in his study of how people make decisions. He started with how somebody controls an airplane in a dogfight, up to long-term decision-making, and show that you have that same basic set of steps. And that cycle, the cognitive cycle, is essential for putting together all these other pieces. So that's basically, and here's how it all fits together. There is, instead of having Charles Peirce in the middle, I put a computer in the middle. And the point is that each step, the induction, neural nets can be very important. Bayesian nets, pattern recognition, very important for your induction step. Then you need various kinds of methods of knowledge discovery, data mining, and so on. That's your abduction step. Then you need belief revision steps for tailoring that theory. Then planning systems and inference engines, theorem provers. You make a prediction. Then you have various kinds of stimulus response, CAN procedures, perception action cycles for acting upon the world. So the point is that We can have multiple algorithms at each step, but the point is that the cycle shows how the various low-level algorithms are integrated in order to do the whole thing. So that's the basic point, is that you need it. Creativity really comes in the abductive stage. That's where the most important part is. And language is very important for this. And so the future directions for AI, what you need is to integrate your language with perception, with action, and with all the different stages of reasoning. So that's the basic point that I want to make. It all fits together in a large cycle of cognition. So that's it.
Thank you very much for great talk. And now we have time for questions and comments, so please.
Well, I guess I answered all the questions.
Any questions? Yes, please.
It's a kind of a observation. I'm doing things in software engineering, in the methodology of software development, and there was a kind of a movement towards, and it's still alive actually, towards multi-paradigm programming. And so I see a great parallel in what you talked about within this. It's kind of a, not artificial intelligence, but a way of finding to do with things in real software development. And it requires applying multiple paradigms, and we are now aware of or coming to this multi-paradigm thing through improvements of programming languages. So recent additions to Java, for example, are functional programming. So that's kind of the same thing. I think I see this is actually kind of what's been known in programming, that you need multiple approaches being rediscovered in the area of artificial intelligence now.
Yes, I agree with that, and the our company VivoMind, one of the technologies we've been using was Java and Prolog. We were using Prolog for the complex AI work and Java for the user interfaces, and more recently we moved to Scala, which is a very powerful foundational method. It allows you to use Java programming, and it allows you to mix Prolog. It allows you, so basically what we use is the C language for low-level algorithms that need optimum performance, right? Things that aren't going to change very much. You write that in C. For user interfaces, we use Java. For a lot of the complex AI work, we use Prolog. And but the idea is that we have a message passing method. So that the idea is that message passing is a very general method, and it requires, there's no requirement in the message to know anything about the sender or receiver. The message just says, here's a goal, solve it. And it doesn't say how the system is supposed to do it. It just says, do this. And then we use a variety of methods for deciding which ones to use and so on, and associated and all kinds of stuff. But the idea is that you need a variety of different methods. Now, when I put the slides up on my website, I'll have some references to other papers or things that go into more detail. But I think the short answer is yes, I agree with you that you want to have multiple paradigms. The critical issue is how do you have multiple paradigms and multiple languages with multiple foundations work together. And the short answer is a message that is relatively underspecified. One of the points about the the object-oriented programming languages had methods where the calling program told the call program exactly what method to use. But that's too detailed. What you want to say is, don't tell me how to do it, just tell me what you want, and I'll do it, I'll figure out how to do it myself. That's a better method. Just set a goal and say, do this. I don't care how you do it, just do it. And in fact, send it out so that you can have multiple systems trying to do it, and the first one that comes back wins, but sometimes not every. If you get several coming back, then you need some evaluation method, and to evaluate which one seems to be closest, and you need a variety of different paradigms. Some are for evaluation, some for computing, some for vision, some for logic, some for informal reasoning, lots of different things.
We have one more question from here.
I would like to ask you, how would you close the cognitive cycle in case of Google Translation, for instance? Because you have this example of Google Translate, but is it possible to close the cognitive cycle within such kind of a translation algorithm, or we would have to build a robot which would interact with the word and then you could close the cycle?
Okay, well, the point that Hurst would make is that for absolute, a perfect solution is impossible. And the engineering principle, the engineers have a very good slogan. All models are wrong, but some are useful. And so the idea is that an engineering solution is that you want a solution that's adequate for the purpose, and a solution that solves the problem to the required required tolerance with the available resources, and that includes time. So John Boyd did a lot of work on this area because he was concerned about cycles going from second, where you have to do split-second cycling. When you're in a dogfight with a jet plane with another guy who's trying to shoot at you, you have to respond extremely fast, and you cannot get a perfect answer. What you need is an answer that's good enough for the purpose and largely based on previously established procedures that you put together in the proper sequence to make them work. If you have more time, you can go through more cycles, and the point where you stop the cycling is where you get an answer that's good enough for what you have to do. And usually, you never get a perfect answer, but you stop when you need to respond.
And the last question.
Like you said, the software doesn't grow, the software development doesn't grow exponentially, but the hardware development does. Then my question is, do you think that one day it will be possible to create some kind of a simplified copy of the human brain using the development of hardware and neuroscience, instead of developing very complex paradigms and systems that use many of those? And for example, it would be like a mock-up of human brain and a feedback circuit that would deliver some motivation, and also sensors that would interact with the world, like in the Mr. Albus scheme.
Well, I think that something like that is a good goal, and as Albus said, the ideas that he obtained by studying neuroscience gave him some insights into designing robots. So he did in fact design better robot control systems by using the insights from neuroscience. But the point is, today we are very, very far from achieving that. There is, however, a lot of people are working on that. IBM in particular came out recently with a new single chip that could be used to have literally thousands of these little neural networks on one chip and wire them together into a system that have thousands of chips. So you would really have a huge number of networks, a huge network that would begin to have a complexity that might come close to the complexity of the brain, maybe say within the next 20 years. However, just wiring them together is not going to give you that intelligence. There's a lot of things that you have to do to understand how they work. And today, the more that the neuroscientists discover, the more they admit they don't know. And so everything they discover opens up more questions that need to be analyzed. So the question is, some people were saying, oh well, in about a few more years, by say 2030, we will have the amount of complexity in our computer systems will rival the complexity of the brain. But we still won't have the same organization as the brain because we still don't know exactly how the brain works. So I would not, some people have predicted 2030 is the time when we'll have the singularity, when the computer systems will rival the human brain, and I think that's much too close. Maybe by the end of the 21st century, something like that might happen. I don't know. But in any case, studying neuroscience, psychology, philosophy, all of those things contribute.
Thank you very much. Thank you very much one more time.